so let's do another proof here from 7.4. This is number 3 in your exercises. And so we have to decide initially then if we're going to use indirect or conditional proof on this. We look at the conclusion here, and of course we'll notice there is no horseshoe in that conclusion whatsoever. So there's no obvious way to do a conditional proof, so let's go with indirect. And so what we do is we indent, and we're going to assume the opposite of the thing we're trying to get, right? Now, I want to warn you that in predicate logic, like we often have a lot of tildes flying around, and they're on one side of a quantifier or another side of a quantifier. I want to make sure you understand that the guaranteed way to get the opposite of something is always put a tilde out in front of it. So this is our assumption for indirect proof. Tilde for all x, tilde ax. And what we're trying to get then is a contradiction, right? We are trying to get a contradiction when we do indirect proof. Now just note here, unlike the proof we did in the previous video, here we don't have any free variables, right? This here is an x, and it is bound by that quantifier there. So there are no free variables here at all. So we don't have to worry about, we can do ui or ug, certainly ug at any rate. While we're indented here, ui is fine as always. So we'll note that. I like to use my assumption right away if I can. I'm looking for a is up here in my premises, and of course there's an a there in the first premise. But the difference here between 1 and 3 would be the quantifiers, right? So we can't use them together yet. I also just want to note here, just because it's worth reminding you, that if you look at number 1 here, the main operator of number 1 is the horseshoe, and so we cannot pull off those quantifiers. They will not come off, so we'll leave those on. But we need to get the quantifiers to match, and of course we have a rule to do that for us, the quantifier negation rule. And so in this case, we can use the quantifier negation rule like so, right? When you have tildes on both sides, we just drop them, and that changes the quantifier. And now, of course, with 1 and 4, we're looking at here in 1, P, horseshoe, Q, and down here in line 4 is our P again, so that's the setup for modus ponens. So modus ponens lets us write down our consequent there from line 1. That's modus ponens 1 and 4. All right, we're going to keep number 2 in mind, because number 2, right, we know we have to use all of our premises at least once. Number 2 has a C in it. Number 5 has a C in it. So I'm thinking in terms of getting our contradiction, it's probably going to involve the C predicate, because that's the only time we have something that matches. And of course, in number 2, it has a tilde. In number 5, it doesn't. So maybe we'll be able to get our contradiction that way. But of course, we would have to take number 5 and break this down then to isolate the C, and that way we can have a contradiction. So we cannot, of course, do simplification on number 5 here, because the main operator of number 5 is not the dot, it's the quantifier. So let's get rid of the quantifier with EI. Right? And when we do EI, we can never choose a variable here, so we have to choose an individual constant that does not appear previously in the problem. This problem doesn't have any individual constants, so choose any one you like. We'll just stick with A here. Once we have this, the main operator is the dot, so I'm going to do com, and then I'm going to simp off the CA so I can get, work towards getting a contradiction with number 2. Right, always remember that you have to do com here to get the CA on the left-hand side, and then once you get it on the left-hand side, then we can simplify. Okay, so simp on 7, we get CA. So on line 8 here, we have CA. On line 2, we have tilde, there exists an X, CX. Seems like we can work out a contradiction there. So note, this is an important thing to remind ourselves. Number 2, that quantifier will not come off right now, right? The main operator of number 2 is the tilde. And if the main operator is the tilde, the quantifier cannot come off. We could work using quantifier negation here to move the tilde out of the way and then remove the quantifier. And that would work. That would be an option. It will take an extra step in the end to do it that way. Instead, what we can do is we can always do EG. So we can do EG on line 8. To get there exists in x, cx. And of course, now with 2 and 9, that's going to be our contradiction. So I'll put it together over here. So line 10 is still indented. We're going to have there exists in x, cx dot tilde. There exists in x, cx. And of course, now that is a contradiction. It's something, a dot, and the same thing with a tilde in front of it. And so now, with indirect proof, it works exactly the same as it did in Chapter 6. Once you get a contradiction written there, you unindent, and then the procedure is always the same. You simply write down your assumption again. And then you put a tilde in front of it, like so. So we will remember that when we did indirect proof in Chapter 6, we often had to end by doing a double negation step. And to match our conclusion here, we will, in fact, need to do that. Oh, I forgot to write down indirect proof. Excuse me. That's lines 3 through 10. And then here we're doing double negation on line 11. Match our conclusion. Okay? So I think as you saw here, indirect proof really went the same way as it did in Chapter 6. And so just remember that maybe the one challenging thing with this problem was to get the opposite of your conclusion here, you want to simply add a tilde to the far left-hand side. That will guarantee in every case that you have the opposite of the conclusion. And that's your safe bet for in the end, getting a contradiction and then getting the result that you want to get.